Okay, one of the things we've talked about before, at least I think we've mentioned it, but never talked about in class. Okay, for anyone who's ever had to move materials from point A to point B, whether it's for your workplace or maybe for your residence, if you have a moving truck, okay, how can you make work much easier for yourself? And what does it say up here, I believe? Well, you could use a machine, which that of a ramp would be that type of a machine that would make work much easier. Yeah, two-wheel dolly carts, I think you call them. Awesome, thank you. Okay, so upon looking at this, why would you use that dolly cart to put something in the back of the truck and not just lift it up off the ground? It's a lot easier. Okay. Sounds like Morse code. And one of the aspects that we do, notice that on the bottom line it says what work done for lifting an object depends on the change in height of that object. So what that's talking about is using that ramp, because if we take a force times a distance, what are you calculating? You're calculating work. Okay, so in this case, on that far right of that whiteboard, we got a couple new formulas for you that used to solve different or various types of story problems. So in certain cases, when like a loading dock or ramp, that's why you see these inclined planes, because it just takes a lot less work. Okay, if you have those dolly carts to take off your truck and then push up that ramp, it's so much easier to do that rather than lifting that up off the ground and then putting it up on the concrete and then moving it again. So an inclined plane is utilized for that. And we've got one here on the east side of the school, and well, we just call it the loading dock. That's outside of Ms. Aaron's and Mr. J's room there, to where you have this inclined plane, and that's so when you're pushing these two-wheel carts up, that it's so much easier to do that as opposed to even trying to pull that up on top of the concrete pad. Can you take that cart and go upstairs? You can, but it's not very easy. Okay, because the wheel has to go around all the different shapes of that stairwell. So it makes it a little more difficult to do. Yes, it can be done, but if it's a nice smooth surface of an inclined plane, it's much easier to do that. All right, so I think this is where we begin, correct? We didn't start here because we have this, right? Done. Okay. All right. I think maybe just one more. Yeah. Little. And one way to maybe try to make sense of this, when we had talked about that static friction and sliding friction, we saw part of a video that dealt with that. Does anyone remember what examples we used for that? The Egyptians, that's right. When the pyramids, we theorize, when they were built, a very long inclined plane was used. And the reason for that is when you make that inclined plane longer, it's going to take smaller amount of work to push it up or pull that up that inclined plane. So it makes work easier then. Now some of you, once we get past this chapter, you won't ever look at this information again or use this information again unless you plan on taking high school or college physics. Does that sound like fun? Yes? No? If I'm correct in this interpretation, we said, who would rather be somewhere else other than this room at school at this time? And I think a lot of hands had gone up. Okay. Well, it's not everybody. We're making improvements. Yes, we hope. Okay. Fair enough. Well, we try to make it interesting. At least we hope so. Okay, does everyone have this information that wants it? Okay, so what we want to do, put some of this to use. Okay, so you don't need to draw this triangle, but we do want you to put these two formulas down on your formula sheet. Okay. And again, notice if you take a force times a distance, what are you essentially solving for? Work. That's right. So when we talk about work input, we set that equal to work output. And do you think, is there any machine out there that is 100% efficient? And the answer to that would be no. So what might slow something down, like as far as pulleys are concerned, or any type of that type of a machine? If you have two metal objects coming in contact with one another, what's going to slow that down? Friction. That's right. So friction is going to slow that down and make it less efficient. Okay? So a lot of motors are possibly up to 90% efficient or something to that effect, but there is no machine out there that is 100% efficient. Okay, so if we're looking for efficiency, we're usually talking about an inclined plane with that. So what happens is you have to put a type of effort into a system. Like, for instance, when you saw those Egyptians pulling that sled up a ramp, okay? What they're doing is you're putting a certain amount of effort, pulling it up that ramp or pushing it, what have you. So that's the effort force going in this direction. What's pulling down on that? The force of gravity. Well, gravity's not a force, but those blocks had a mass. Gravity was acting upon it, so that's why we say the force of it, because again, that mass times acceleration would give you that force pulling down. So the height of the ramp, that's going to be your resistance distance. In other words, you're fighting gravity from the bottom of that ramp to the top. So that's your distance resistance. And then the force that's going in there again is mass times acceleration gives you your resistance force. Okay. So let's see here. So if we wanted to know this, use this color. What is the efficiency? I'll try to keep this short. So that's its length, and it has a height of moving heavy equipment. You're saying it's a bulldozer? Okay. So go ahead and write that information down if you choose to, and we'll start plugging the variables in where they belong. Okay, our lights glaring off that or reflecting off and making it hard to see. Okay, so we'll try this again. Is that better? Okay, here we go. Here comes some lights. How's that? Good enough for now? Okay. Okay, and this problem probably looks difficult because you haven't seen anything like this, but we know that if something is labeled in newtons, what's that referring to? That's referring to your force. And if it's measured in meters, we know that is a type of distance. So to calculate efficiency, we have to have two forces and we have to have two distances. And notice in this problem, what are we possibly missing? We've got our effort force, because let's say, for instance, there's a winch that's pulling this heavy equipment up that ramp to be loaded onto a semi-trailer. So this winch may be, I don't know, 40 horsepower, 50 horsepower, either one. So what we need to know is we're missing one of those forces. But if you have a mass, that 900 kilograms, can you find force with that mass? What do we, with that box on that ramp, we said there's an arrow pointing down. What is that possibly illustrating? The gravity acting upon that mass. And if we have the mass and the acceleration, you can solve for what then? You can solve for force. There's the second force that we needed to find. Okay? Resistance. Okay? So you have a resistance force, that's what F, little subscript R, and then F of with a little subscript E means effort. I probably didn't describe that, did I? My apologies. I meant to point that out. Okay. So looking at this winch is applying 8,200 newtons of force. Okay, either that or you could say the Egyptians were pushing, pulling, and putting an effort into that block of sandstone, pulling that up. So that means they had to put effort into it. So that is your effort force then. Again, this probably looks difficult because you haven't seen anything like this yet. Okay, so that's why we'll take this nice and slow, and hopefully it makes sense of this. So we need, if we want to know this efficiency, how many variables do we need to know? We need to know 4 of them. Okay, so let's start putting some of these where they would belong. We need to know a resistance force. We need to know a resistance distance. We need to know an effort force. We need to know an effort distance. Okay. So, in other words, if this dozer was 8,900 kilograms, okay, and you correctly said what is pulling down on that bulldozer? Gravity is, which has 9.8. And how do you label that? So if you have an acceleration in this mass, what would you do with those two numbers? And that's going to give you a what? Right. But which one is that going to be, a distance or a force? Yeah, it's going to be a force. Okay? So 8,900 times 9.8, you said gives what? 87,220. Okay? Again, that is newtons. Okay? So that winch is pulling that dozer up, applying how much force to it? 8,200. Okay? Okay? So, for how long is that winch pulling that dozer up that ramp? For how long is it pulling it, do you think? What does it say in the problem? 26 meters. So for all them 26 meters, which is an incredibly long ramp, I get that. This is just a problem as an example. It's pulling that up this ramp. So that's going to be your effort distance. That's how long that winch is pulling that up that ramp. Okay, so 26 meters. Okay, and then this is a resistance from gravity. So what is the height of the ramp then? Not how long it is, but how high it is. 2.5 meters. Okay? And when we get some of these story problems, you're going to get better at this. And the example I always like to use, okay, ladies in volleyball. We can use basketball too. Just think of the first time you had to go from serving like this to up it goes and away it goes. Was it going to be really easy that first time? Maybe going into the net, maybe airmailing it onto the stage or something to that effect. It's just new. It's a new challenge that you have to probably overcame and probably quite good at it now. At least we hope so. But it's something that it comes easier for some people more than others. Now, once we have this information down, now we can just put these in where the equation tells you to. Okay? So, what are we putting on top of this fraction according to our equation? Okay, so 87,220 times what? 2.50. Okay, so what goes on the bottom here then, according to our equation? 8,200 times what? Okay. So now the best way to do this, okay, is with your, when you have this in your calculator, multiply your top two numbers. Okay, so 87,220 times 2.5. That gives you 21,805. No, I'm looking at the decimal in the wrong spot. 218,000. Sorry. We've got efficiency equals 218,050. Okay? So what do we, and we're going to multiply those two numbers, 8,200 times 26, 213,200. You know what, I think I goofed. I think I put the decimal on the wrong spot. Let me just check something. 8,200 times 26.5. That's a little closer. But the problem with this is when you divide that, what are you going to get? You're going to get 1. We said you can't get over 100% efficiency. So this wasn't quite worded correctly. So I'm just going to make this 219,000. Okay? So now when you divide that out, it's going to give you 218,050 divided by 219, 200. Gives you 99.99. That's a percentage. Just take it times 100. I see a lot of disgruntled looks out there. Are we confused on this? Or yes? Okay. This right here, you're taking the resistance force. Oh, that is, for instance, if maybe you're using a hydraulic jack. You're putting effort into it, okay? An effort force going down, okay, is going to have a resulting force of going up. We're going to see that in a video here just shortly. That does not apply to this. No, sorry, because we're looking for an efficiency. Because it's asking for that up here. That's why we say EFF. Okay. So maybe the best way to solve this would be, let's say maybe it's 30 meters in length. Okay. So now if we take 82,000 or 8,200 times 30, that gives us 246,000. Right. Okay. So we're changing the length of this ramp, saying it was 30 instead of 26. Now that puts 246,000 down here. Okay. Left outside, we're good. We're good. We're good. We should do another one. Yeah. Okay. Left middle. Left middle. Okay. Middle. Good. Good. Okay. Right middle. Right outside. Right outside. Right outside. Right outside. Are we good? All right. Oh. So when you get this, it's 88%. Okay. All right. Can we erase this? And I don't have a paper to hand out to you or for you. Would you rather go over another example or wait till Monday to hit it again? Another example right now? Okay. Okay. So we'll have to shoot from the hip. All right. out here. Okay, go. Who can we pick on in here? No, we've done that before. Okay, so what do you need to move from your garage or your house? You're gonna put something on display. Car. Yes. Just for ramps. Yes. So, what are you moving? Okay, an arcade machine, and is it really heavy? Okay. So, if we took, see, I need to write these numbers down here. Okay. I find it hard to believe it would be 3,300 pounds, but we're gonna say it is. Okay. Did you eat your Wheaties this morning? Did you eat your Wheaties this morning? Okay. So pick a friend. Tanner, did you eat your Wheaties this morning? Okay. Well, to make things easier, this type of cereal, breakfast cereal. Okay. So you got this really, really heavy machine, this arcade machine. Maybe it was full of quarters or something. I don't know how many quarters they're supposed to hold, but there's a lot in there. Okay. So you want to move it up this ramp. Okay. So you and Tanner, you're grunting and groaning, and you're putting all the force in that you can. Okay, so what is the efficiency then? Okay, I don't mean to put that redundantly, but just made this problem up just now. Okay, because we want to try to come up with good numbers for you, unlike that last one. And I probably fall in the same pitfall every time. Okay, so upon looking at this, where do you think you can put some of these variables into? So we said them two are grunting and groaning and pulling and pushing and yeah, so they're putting that much effort into it. So that's 1,600. Okay. What else? So nope. So how long are they? Oh, I'm sorry. You say effort or distance? Long is DE. So this is your effort distance, 15. Okay. So how high is that ramp? That's DR, so that's 1.50. Okay. So how did you get that? Okay. So 1,500 times 9.8 gives you what? 14,700. Okay. Okay. So we know we should have our forces in the right spot because they're measured in newtons. Okay, so that ramp was 15 meters long, so that's how long you're putting that effort into it. And then finally, from the ground to the top of that truck was 1.5 meters, so somewhere about right in here. Okay, so now the hardest part is getting these variables in where they belong. So how do we finish that? Okay, so our efficiency then equals, what do we do with these two numbers? Okay, so 14,700, okay, times 1.50, and what's on the bottom then? And what do we do with them two numbers? Okay, so again, if we take 14,700, so yeah, 22,050. $24,000? Okay, so once you get it down to here, and what do we get for an efficiency? 91%. It gives you an answer of 0.91, but you got to take that times 100, because that's your efficiency then. Okay? Repeat that. Well, 92% is fine. All right. All right. It's not our intention to mislead you like that last example, but and again, it's one of them aspects you're going to get better at this the more you work on it. Okay. Any questions before we stop for today? All right. So we will continue with this on Monday. All right. Catch up to you next time.